Hello friends, now in this video we will learn about the different methods of the preparation of alcohols, right? How we prepare alcohols. Number one is we can prepare alcohols from alkenes. From alkenes we can get alcohols by different methods, and one of the method is acid catalyzed hydration. Hydration basically means addition of water. So when you add a water here across a double bond, so the double bond breaks here, pi bond breaks here, one carbon gets hydrogen, the other one gets OH, and you get the alcohol. And normally the hydration of the alkenes is very slow. You can increase the rate of the hydration by adding some acid. So here in acidic medium the reaction is quite faster. Here the acid acts as a catalyst, right? If you look at the mechanism of this hydration, if you look at the addition of the water across the double bond, so basically this is an electrophilic addition reaction. And here in this reaction what happens, first of all, the double bond is under the attack of the proton, right? And what you get, for example, you get an intermediate there. One of the carbon atom gets a hydrogen here, the pi bond breaks, and the pi bond forms actually a bond. There was a double bond here, right? And now this electron pair will shift towards this hydrogen here, right? And it will form a double bond. It will form a single bond here, right? Between the carbon and the hydrogen. And then we get an intermediate, a carbocation, right? So a carbocation is formed here as an intermediate, carbocation. This is the step number one. In the second step, the same carbocation is now under the attack of the water molecule. Water here acts as a nucleophile because of the lone pair of electrons, right, on the oxygen atom, right? Over here, it will attack on it, and therefore you get an intermediate here like this. H, carbon, and then oxygen, two hydrogen atoms there with a positive charge now on the oxygen, and then from this intermediate hydrogen will be lost as an H plus, right? So what you get a carbon with the H and another carbon with the OH. So overall, if you look at this reaction here, it is the addition of water across the double bond, right? So double bond over here breaks, and one carbon gets hydrogen, the other one gets an OH. And the important thing to remember here is that the intermediate during this reaction is a carbocation, and we know the order of the stability of the different carbocations, right? The tertiary carbocation is more stable than secondary, than primary. This is very important, right? We'll just do a couple of examples on it, and we'll see what is the difference, what will be the difference due to the formation of the different types of carbocations during this acid catalyzed hydration reactions. So here it is. The net reaction is that addition of water occurs here in acidic medium, and you get alcohols from alkenes. One carbon gets hydrogen, and the another carbon gets hydroxide. Now what if we have an asymmetrical alkene? Asymmetrical alkene is the one where the groups attached to to the two carbon atoms are different. Suppose here if you got hydrogen and the hydrogen here and the hydrogen here, this is ethene and this is a symmetrical alkene, right? So for symmetrical alkenes you only get, there's only one possibility of a product. You only get one product, that will be the ethanol, right? CH3 will be this carbon and this will be CH2OH. So you get one product only. But what if you have asymmetrical alkene, where the two carbon atoms, they got different substitutions attached to it. Suppose you got here hydrogen, another carbon gets hydrogen and the methyl group. So if you have asymmetrical alkene, how does the addition occur? In asymmetrical alkenes here, the addition takes place in accordance with the Markovnikov's rule. So let's take here an example. If you got a carbon-carbon double bond, now this is asymmetrical, means it has different substitutions. Suppose this carbon got two hydrogen atoms and this carbon got one methyl group and the hydrogen atom. Now this is an asymmetrical alkene. And when you add the water here in acidic medium, when we do the hydration to this asymmetrical alkene, the addition follows the Markovnikov's rule. According to the Markovnikov's rule, the hydrogen will add to that double bonded carbon, right? Double bonded carbon that has more number of hydrogen atoms. So if you look at this particular carbon here, it got 2 hydrogen atoms, and the other one, it's attached with 1 methyl only. Correct? So therefore, according to Markovnikov's rule, hydrogen is added to that double bonded carbon, double bonded carbon with more number of hydrogen atoms. Correct? Hydrogen from the water, okay, that will go to the double bonded carbon with more number of hydrogen atoms. So that means this particular carbon gets hydrogen and this particular carbon will get hydroxide. Okay, so when addition occurs, double bond breaks, this carbon gets hydrogen and this one gets hydroxide. So therefore the product will be, it will be the CH3, C, H, OH, and then now this carbon is now CH3. So you get the 2-propanol. You also get the 1-propanol, but the the quantity of the anti-Markovnikov's product will be very, very less. That will be that will be a minor product, right? The major product here always is a Markovnikov's product. This is a Markovnikov product, right? That means it is formed in accordance with the Markovnikov's rule, which states that during the asymmetrical alkene, right, during the addition of an asymmetrical alkene, the hydrogen, or you can say the positive part or the electrophile of the reagent, attacks to the double bonded carbon with more number of hydrogen atoms, right? So the electrophile here is actually the H plus, and hydroxide is the negative nucleophile. According to Markovnikov's rule, electrophile attacks to the double bonded carbon with more number of hydrogen atoms. So that's why this CH2 will change into CH3 and the central carbon gets a hydroxide there. Now why, right? We can ask why the addition occurs as per the Markovnikov's rule. Why should the electrophile attack on the carbon with more number of hydrogen atoms? It's because the intermediate that you get during this addition reaction will be a more stable carbocation. Let's take an example. The same molecule here. What if we add, suppose, the carbon atom on the CH2 group here, right? Suppose here, when electrophile attacks, right, on it, and the hydrogen is attached to, it goes to this particular carbon, right? So what do you get? You get a carbocation over here, and the carbocation will be CH3H, and over here this is the carbocation, and then this, the CH2 will change into CH3. This is as per the Markovnikov's rule. Hydrogen goes, or the electrophile is added to that double bonded carbon with more number of hydrogen atoms. This carbon has got 2 hydrogens, this carbon has got only 1 because it has a methyl. So you got here a carbocation which is a secondary carbocation, 2-degree carbocation. Okay, you got a 2-degree carbocation. And if the hydrogen doesn't go here, what if the hydrogen goes to this particular carbon, the one with the less number of hydrogen atoms? In that case, the carbocation will be formed over here, right? And then means the intermediate will be like this, CH3, and the central carbon will be now CH2. The terminal will be the CH2 positive. Now this is a 1-degree carbocation, right? So here is the reason. Secondary we know is more stable than primary, because we know the order of stability of the different carbocations is tertiary is more stable than secondary than primary carbocation. So hence, when addition occurs, the electrophile attacks first to that double bonded carbon that produces the more stable carbocation. There are 2 possibilities of the carbocations, a secondary and the primary, but secondary is more stable. That's why it will be formed as a major product. And then from this molecule, when it is the hydroxide which attacks on it, right? Okay, hydroxide group attacks on it, and what do you get there? You'll get the CH3, COH, H here, and the CH3. And from this 1 degree carbocation, the product that you get will be actually CH3, CH2, CH2OH. This will be 1 propanol and this one is 2 propanol. Now let's take another asymmetrical alkene here. For example, this is our alkene CH3C, H3, H, and this got the CH, double bond CH2. This is an asymmetrical alkene, and when we do the hydration here in the acidic medium, we know the first attack is from the electrophile. The H plus sign that will attack on the double bonded carbon, right? With the more number of hydrogen atoms over here, it will go to this particular carbon, right? So the pi bond will break and it will form a bond with the hydrogen, and the bond will be with this CH2 carbon. So CH2 will change into CH3. So what do you get here? This is as per the Markovnikov's rule, right? The hydrogen goes to the double bonded carbon with more number of hydrogen atoms. So you get the CH3 here, CH3, H here, and then the CH, and then you get a single bond CH2. Now it will be CH3. This is the carbocation that you will get, right? As an intermediate carbocation, right? And we know that when, suppose here, from this molecule, in the next step, in the second step, it is the hydroxide, or you can see the water molecule that will attack on it, right? On it, and you get a product like this. You get the CH3, C, H3, H here, and then H here, OH will be here, and the CH3. That means overall, the addition occurs as per the Markovnikov's rule. Hydrogen goes to this one, hydroxide goes to this particular carbon, and you get the OH on the second carbon. But look at this, intermediate here. This is actually a secondary carbocation, right? This is a 2 degree carbocation. But carbocations actually have an important property of rearrangement. If there is a possibility for a carbocation to get a more stable carbocation, then it will rearrange. Okay. So carbocations can undergo the rearrangement. They will rearrange so that they can, get a more stable carbocation. Here in this case, due to the hydride shift, hydrogen with both electron pairs will shift to this particular carbon, and then you get an intermediate, another intermediate where you have a positive charge on the tertiary carbon. So that means you get a tertiary carbocation. This particular carbon now will get a positive charge, and the carbocation will be a tertiary carbocation. Now this is H here, and this is the CH3. This particular carbon is a tertiary carbon, right? Carbocation. This is a 3 degree carbocation. Okay. Secondary is less stable than tertiary. We know it, right? So basically, for the hydride shift here, the driving force is actually the stability of the carbocation. Basically you get a more stable carbocation. That's why this hydride shift occurs. The hydrogen from this carbon, it shifts to this particular carbocation, with both electrons as an H negative. That's why it's called the hydride shift, right? Not the hydrogen shift. This is the hydride shift. So you get a more stable carbocation, and from this more stable carbocation, when the hydroxide attack occurs, and on this particular carbon, and you get the CH3, CH3 here, and the OH will be here, and this will be the CH2, CH3. And when you look at the two intermediates that you get here, the secondary and the tertiary, basically in the reaction mixture you got both, right? First, due to the addition of a hydrogen on it, you get a secondary carbocation, but this is a secondary carbocation rearranged to the tertiary. In the reaction mixture, we have both secondary and the tertiary, but the secondary will be lesser in quantity, in percentage, than the tertiary. That's why this is the major product that you get, and this will be the minor product, right? These are the two products that you get from the hydration of this asymmetrical alkene, and the two products that you get different here is because of the hydride shift. Hope you got the concept. Thanks for watching the video. Bye for now.